All right, number 3. Each croquet bottle is each croquet bottle in a set has a mass of 0.5 kilograms. The green ball, traveling at 12 meters per second, strikes the blue ball, which is at rest. Assuming that the balls slide in a frictionless surface and all collisions are head-on, find the final speed of the blue ball in each of the following situations. So we're always solving for the final speed of the blue one. Okay, so part A, the green ball stops moving after it strikes the blue ball. Okay, so we know that here momentum is fully transferred. Fully transferred from green ball to the blue ball. So whatever momentum was in the green ball is now in the blue ball. How do I know that? Because after the collision, the green ball completely stops moving. And we know that momentum can't just disappear. So whatever momentum was in the green ball must be transferred to the blue ball. Now, we know that the mass of the green ball is equal to the mass of the blue ball, which is 0.5 kilograms. Because of that, we know that initial momentum is going to be my handwriting is getting pretty bad here. Always. Okay. So if the green ball stops, all of the momentum goes into the blue ball. So the velocity of the blue ball, you can actually do this just through logic. You don't even have to do a calculation. If I solve this setup for velocity, right, I'll have, what is it? Momentum over, what is it, mass? And so I just figured out the momentum. I'm going to put that in for that. I'm going to divide by the mass. Again, I have a situation where I have a kilograms divided by kilograms, so that goes away. And I end up with 12 meters per second. Now, this makes sense because the green ball was originally moving at 12 meters per second, right? Did I make that up? Yeah. And so if the green ball comes to a complete stop and they have identical masses, means that after the collision, all of the momentum has been transferred to the blue ball, and so that means, because they have the same mass, that the velocity will be the exact same as well. Again, you could have done that in your head, but it's always a little bit more safe to actually go through the calculation. Now, what if the green ball doesn't come to a complete stop? It actually continues to move here. So, part B, the green ball continues moving after the collision at 2.4 meters per second in the same direction, right? So in the same direction. Don't get ahead. Okay. So again, we know what the initial momentum is, right? We can kind of just steal it from our previous calculation. All right, so we know that the initial momentum is 6 kilogram meters per second. And so we can set up the momentum equation. So we know that momentum is going to equal mass times velocity. It's green, plus mass blue times velocity blue. Okay. And in this situation, I know what the momentum is. I know what the mass of the green ball is. I know what the mass of the blue ball is. I know what the velocity of the green ball is after the collision. So the only thing I don't know here is the velocity of the blue ball. But again, that's what we're actually trying to solve for. So I'm going to rearrange this equation to solve for velocity of the blue ball. And so I'm going to get velocity of the blue ball is equal to Can't do that in my head, apparently. We're going to have... I don't want to do that. I want to factor out masses because they're the same. There's the mass of the ball. Now this is going to work out 9.6 because you can kind of see how this works. Both of these added together is going to equal your 12 meters per second. And the only reason that works when conserving momentum is because the masses of both of the balls are the exact same. Otherwise, you would not be able to add up those velocities. You get velocities that do not add up to that initial 12, but because the masses are the same, that's what you get.